I'm James Honaker. I was going to point out Vito, but I think he's just popped out now. So I work at IQSS, which is this building. I'm one floor up on the west side. I'm a research scientist here with these guys. Let me think. Okay, so the Institute for Quantitative Social Science, that is an interdisciplinary group. It's not really a part of any department, but it is in the Faculty of Arts and Sciences here. And it brings together affiliate faculty who do quantitative work. So there's an emphasis on social science, but it's not only social scientists that work with us. We do a lot of work with people in the School of Public Health and people in the school in the medical school. We work increasingly with the people in the astronomy department. So it's more that we, so there's more of an emphasis on quantitative than on social science, although also there are centers in IQSS that aren't quantitative at all. So exactly what it is, I think sometimes it's referred to. There have been thoughts about expanding it to the Institute for Quantitative and Qualitative Social Science and Other Sciences. It could just be the Institute for Science at some point. But it's as a group, it has a deep commitment to scientific explorations of questions that generally involve individuals and stars. So the fun part of my job is that I get to work with a different set of people in each project, and sometimes a different set of people every day of the week. I work in the data science group, which is run by Mercedes. She would be here, except across the hall we're meeting with all the different people who work in Dataverse. Of all the people in the building who could talk about Dataverse, I'm probably the least qualified, but they are all in the other building. So hopefully there's not an explosion over there and I'm the only person who's left who knows Dataverse. However, I will talk about Dataverse today, and if you have more questions, you'll learn more in the future community meetings. And I use it a lot, but I don't stick my hands into the Dataverse code very often. The Dataverse project is the latest version of a long history of projects here at Harvard and in IQSS and the things that existed before IQSS for archiving, saving, preserving social science data, and also making it open to the research community for replication. So at the heart of good social science, good science, right, is the idea that anything that you do scientifically, it should be possible for other people to replicate exactly what it is that you did, okay? Perhaps by collecting new data and running the same process, or perhaps by examining the data that you have if it's observational and can't be replicated. We don't want to replicate World War II too many times, so we'll just stick with one version of World War II for now. But whatever the data is that's been collected should be open to other researchers to be able to investigate the ideas that you've come up with and see how robust they are or whether you can expand them. And so that requires that data is preserved in the long term. It's often the case that when researchers haven't been playing with a data set for a month or two, or a year or two, or a decade or two, they forget where it is, or they forget what file format it exists in. And it's arduous to make that constantly available to other researchers who might want it. So putting it into a repository, right, where every time file formats change, it's automatically upgraded to new file formats, where if people are trying to investigate the data from different perspectives using different tools that have their own file formats, it's translated into SPSS or into Stata or into R or into Excel or whatever it is that you're using to investigate that data. Also, providing a method for citing data. Another central tenet of sort of good science is not only that data is open, but that people who collect data and use it have an incentive to share it. Okay, so the coinage of academia is citation, right? If I write good articles and other people are using my work, they'll cite me and say, my work is based on this work, which has already proved some things that I need. Similarly with data, if people are using data that other people have collected, good principles should say, I'm going to be using this data, which I didn't collect myself. Or I've added a few years of data to this other expansive project that somebody else used. But there's no there normally to cite for data, right? So normally citation has typically been about articles, right? People have written things, books or articles that exist in journals. They're published. Those have a citation to them, but the data itself is just this sort of nebulous thing that it's hard to keep track of. And so sometimes there's an article associated with the data that's sort of a placeholder for the data itself. One of the key things that Dataverse does is provide a DOI, a thing that's firmly fixed to that data set and exists for all time that can be used as a citation. So I use this data set and I merge in a few other variables. I can say, these are exactly the data sets that I've used, and I have a persistent link that anybody else can follow that DOI and find that data set at any other time. And those citations, accumulate, and the scholar who created that data is now being cited for a product, an academic scholarly product that they've been creating. Okay. And then also, in addition to Dataverse, IQSS spends its time, has a bunch of people who sort of work on statistical methods and quantitative methods more broadly for analyzing social science data and sort of tackling the kinds of endemic problems that broadly social scientists or people who have observational and experimental data stumble onto. So I often work in problems of missing data and measurement error, which are two classes of problems you often get when you're trying to observe individuals and collect corpora of data on them. I've been working on privacy with this group for over a year now, I suppose. I always think about how old my daughter is and then add 2 months, and so it's like, which of those two projects is more important to me? It's hard to say. So here's Dataverse. Let me give you a sense of it.
Keeps you up at night.
Yeah. Which one screams at me more? When I don't do what they want. Okay, so here's the architecture of Dataverse. Dataverse is going to be a repository so that individuals have data sets. They want to make it open. They want to be good scientists. They want to make the data open to other people. They want to be cited for what they've already done. They want other people to extend their work. They want other people to maybe validate that their work is valid. Also, they want to get funding from the NIS, for the NSF, or the NIH, or any of these funding agencies, Ford, who normally attach writers and say, well, look, if we're paying you for to collect data, out of a public grant, then that data belongs to the public. And so the data needs to go somewhere and be made available. So Dataverse is a repository for doing this and abstracting that process and making sure that users don't have to keep the latest version of their data set on available in some crazy way. Here's the architecture. You can think of, you'll hear these things called Dataverses. This is Dataverse 4.0, came out just a month and a half ago. There's a slightly different architecture that Dataverse now uses. There are these, think of these, a Dataverse as being a container in which you can put things, okay? So we'll talk about Dataverses. A Dataverse is really just sort of an abstract location for things to exist inside. Dataverses themselves might be put inside Dataverses. So if you want to think of it somewhat as a folder structure that has all of these attached tools to it that keep whatever is in the Dataverse persistent and converted across time and has a citation link. And then inside Dataverses also, I can put data sets. So I might drop data sets into a Dataverse and other Dataverses into a Dataverse. And in a data set is more like what you might think of as a database, right, from a CS perspective. But it could be a database, but it could also be all sorts of things that are attached and grouped around that particular data set. So a data set might be the files that contain the raw data, but it might also include all of the documentation that you need in order to understand what that data is doing. And that might be in a separate file, or it might be attached to the data depending upon the data format. There might be short and long versions that explain what those questions are. And then also in this nebulous thing called a data set, which kind of looks like a database but isn't, there might also be code that the researcher has made available that explains, I created this figure in my article in Nature, and here's the code that you need to move from this data to generate that figure, or to rerun my analysis and see how I created my estimate. And also metadata. So metadata is a header that comes with the data set that explains what's in that data set. Not the data itself, but descriptions of what the data is and descriptions of what the data means. So metadata might include, this is the size of the file, but it might also include, here are some summary statistics about these variables, or it might include how was the data collected and who collected it. And the metadata is going to be very important to us. The first day of the Dataverse conference over there right now is entirely about metadata and making sure that metadata across different repositories that different people use all speaks the same language. But metadata is sort of how I find a data set that I want to use. It's how I explore across repositories to say, I need data that covers this country in this year and contains economic indicators. Right? That information should be in the metadata. In some sense, that's like the card catalog for that data set. But it might contain lots of other things. And we're using the metadata itself to preserve some of the things about the data that we can make public while shielding the actual data file itself, perhaps in some layering that in a deeper level of security. So those are the things that go into a data set. A data set is a data file at its heart, probably. Also, with some documentation, maybe some code we run on it, and this header file, the metadata. And then data sets go into Dataverses, and other Dataverses might go into Dataverses, and it could be Dataverses all the way down. Okay? That's the basic architecture of Dataverse. Here's what Dataverse looks. You were promised a glimpse of what Dataverse 4 looks like. Here's an example of what Dataverse 4 looks like. I ran a little search on privacy, and it's telling me that there are 3 Dataverses which have privacy in their title. One of them is the Privacy Tools Dataverse here, the Dataverse for this particular project. 384 data sets that came up with a search term in there for privacy, and 241 files. If I hadn't done a search right now, actually maybe I'll click to, if I click to Dataverse right now and open it up, here's what it looks like on a browser. Here's a splash page. Oops, let's see if I can get this to be the right size. Yes, okay. It's telling me that right now there's 58,000 data sets. Most of these are social science data sets. On the Harvard instance of the Dataverse, there are Dataverse instances all around the world, or at least in other universities, including China and Amsterdam, so I can say all around the world. There's a Dataverse instance up the hill at the Center for Astronomy that contains a lot of the imagery data from the astronomical disciplines. There are Dataverse instances that are being set up in the Harvard Medical School to hold lab data from medical files. So we got about 60,000 data sets that are in some nature social science. Most of those don't contain any private information. If people have private information, we sort of say, wait up. We're going to build some tools, then you can bring them here. That's what Dataverse looks like. That's dataverse.harvard.edu if you want to see the Harvard-specific Dataverse instance, or thedata.org if you want to see a splash page for the entire Dataverse project. Let me go back to my slides. Okay, so that's how Dataverse works. In my end, again, I don't necessarily myself. There is a Dataverse team, which you will undoubtedly meet up with. One of you has a mentor with Gustavo, who's one of the lead engineers on the Dataverse project. I work in the Stats and Analytics group, which is slightly separately. And we build tools that sort of, often these tools are wrappers or layers around Dataverse. So Dataverse is at the heart, and then there's some tool that involves some statistical exploration of something that exists in Dataverse. These are some of the projects, for example, that we've built here. These are all examples of libraries in R, so we use R quite extensively. R is a very simple scripting language that's used primarily by the stats and applied stats communities. It's as languages go, it hardly even qualifies as a language. It's really a scripting way of representing the abstract things that statisticians care about. So a simple way of, say, specifying equations and relationships in variables, and then seeing graphs about those. R originally comes out of a language called S. S was created at Bell Labs, just down the hall from when they created C at the same time. So that's the history. C's been around for a long time, and S has been around just as long as that. R is an open source version of S that's a little bit more capable and more broadly used now. So these are all packages that we sort of built, and it's sort of the set of tools that people in my group, the stats and analytics group, care about packages for missing data, packages for matching if you're interested in looking at experiments or you've heard about potential outcomes or causal analysis. Packages for how do you ask surveys and make sure that they're comparable across languages. So, if the World Health Organization goes to a developing country and says, how healthy are you today? And then they go to France and ask somebody, how healthy are you today? How do you make sure that the question means the same in both languages and also the scale means the same? Because if you're comparing yourself to your peers, those might be very different answers. How to deal with, how to make analysis from aggregated data, like in elections, ecological inference problems, how to redistrict, how to cluster documents that qualitative social scientists might create and realize, oh, normally all I do is I read texts, but I've suddenly found I've got 150,000 texts and I'm not going to read all of them, so can I actually do something quantitative? So clustering methods for looking at texts. How to deal with predicting things that almost never occur. So models for rare events. There's a famous paper by Gary on predicting the probability of events that have never happened. And that's a difficult statistical problem. It's not. And then counterfactuals. The best way to, this is an interesting machine learning technique that has been developed here. Called verbal autopsies, which says it's where they've shown, it's generally the case, increasingly true, that statistical models are better than experts in those disciplines for making predictions, right? So that's at the heart of, say, quantitative empirical ways of stock trading that sort of take stockbrokers out of it, or sabermetrics. The statistical model can pick good baseball players that expert scouts were sort of ignoring. This is an example where a statistical model does a better job of predicting why you died than the person who conducted the autopsy on you. So this is ask the people who knew the person just before they died what was going on with them, and run a machine learning process on that, and and you can learn. Well, he was coughing a lot and he was sweaty all the time. You can do a pretty good job of predicting why somebody died, and that's useful in the developing world because in lots of cases, 95% of the population that dies is not going to get an autopsy or even get a cause of death. But if you want to track health trends and understand sort of where you should be shipping antibiotics, you want to know where people are dying. Bayesian forecasting, and then Zelig. So I finally got to Zelig. I probably spent too much time on all the other models that we work on. But Zelig is a R package that sort of abstracts. There's 5,500 different packages in R. R is a giant open source project where different experts in different particular domains might write a package that says, this is exactly the way to implement this statistical model that I just dreamed up last week and only I know about. But I'm going to write a paper about it, and I'm going to create a package that now anybody can do what I just did. Okay, a way of sort of sharing in an open way, open statistical methods. The problem with that is you've got 5,500 different conventions for how your data should be structured and what an analysis model should look like and what your arguments are going to be called. So every time you use a different one of these packages, you have to learn the way, the API that particular person has used, the way of thinking about data that's specific to that person's discipline, perhaps. And so Zelig is a wrapper or a bridging software, a way of abstracting and saying, if you learn one convention, if you learn one way of understanding how to represent a statistical model, then you can connect to all these other packages that you might have to learn individually, separately. So it's a library that allows you to use lots of different R packages, but only use one call structure, common call structure. Also, each of those individual packages might or might not have the exact statistical utility you use depending upon whether it was interesting or useful to the original researcher. So there are lots of sort of abstract statistical tools like bootstraps or constructing confidence intervals or out-of-sample forecasting that are common tools and work across statistical models, but they might not have been implemented in a particular package because that author didn't need it in his work. And so Zelig was sort of like, say, well, here's a package, but you need to bootstrap. Okay, there isn't bootstrap in that package, but I'll provide you one because it's a common language. The reason why this is the most interesting of these packages for this particular problem is that One goal that we've had eventually is then to allow these statistical models that we're developing in Zelig slowly to exist in a privacy-preserving function, a privacy-preserving way. So either the tools that we will develop that report back differentially private statistics might eventually become their own separate model, own separate package in this list, and we'll have a library of tools that exist for statistical models, or maybe they will be a branch of things that you can get to in Zelig, or maybe we will come up with some abstract way of saying anything that's in Zelig we can make differentially private. Those are other possible goals. So we work a lot in R, and a lot of the people who are working in differential privacy will be working in R. It's very nice. It's a nice language to prototype things up. It gets things up and running fast. The applied statistics community uses it a lot. So if you write things in R, other people will be using it. This is Zelig. It's named after a Woody Allen movie. I will give a quick explanation of how Zelig works when we have a more detailed R course tomorrow, I believe. But here's your first R code. If you've not seen R before, it's reasonably simple code. This is all that I need, for example, to run a complete statistical model predicting vote as a function of age and race, and interpret the model in ways that anybody who doesn't know statistics would be able to see, and construct a whole bunch of graphs to explain what my statistical model did. So statistical model in a page, and half of that page was saying, oh, I need to load up the library of Zelig. Okay, so it's a very simple call structure for running statistical models. And you get back from, say, a page like that, a whole bunch of different graphs, visual representations of what's going on in your statistical model. So here's the probability of voting if I am age 36 and non-black. Here's the probability of voting if I am older and also non-black. So my probability of voting just went up. Here are distributions of expected values. Here's the change in the probability distribution that you might vote. So by getting 10 years older, you got 3% more likely to vote, and all sorts of other summary statistics of the statistical model that you just ran, constructed automatically by Zelig. And a lot of these are the style of statistical results that we might also try to make differentially private, right? So present these kinds of graphs in ways that can't be used, can't be attacked to actually learn about individuals, but still give useful representations of the statistical model that's underlying it, even if you can't see the raw data you ran the statistical model on. Okay, some more graphs that Zelig constructs that are really just pretty. So they're there. Last piece of software that I'll talk about today is, oops, sorry. I was trying to see what time it was.
2:41.
Perfect. Last piece of software that I'll talk about today is, are we not working today? Damn it. It's two ravens. Vito's left the room, but Vito and I work a lot on this software. This is an interface for quick exploration and statistical analysis of data that is sitting in Dataverse. Okay, so it on the one hand, it is a statistical interface for running statistical models on data sets that are in a repository. That's a one way of explaining what Two Ravens does. On the other hand, it never touches data, so it doesn't actually know what a data set is, and it doesn't actually run statistical models. So it's an interface for running statistical models on data sets that never touches data and doesn't know what a statistical model is. It is really just an interface, a very thin layer that says, what is it you want from a model, and then sort of abstracts those things away. So it's named after two of the ravens that were companions to Thor. I can explain the story. Sorry?
Why not two dogs?
Why not two dogs? Well, so what the ravens do is the ravens go all around the world, watching the world and reporting back what's going on. Okay, and they're called thought and memory in the original language. Sorry, Odin. To the original language. So they tell Odin what he should be thinking and what he should be remembering. And so the analogy here is that there are these two pieces of the software that are telling the user who wants to run a statistical model what the data can tell him to think about the world, and also what other people who have run similar models to you, this is the memory aspect, what other people who have run similar models to you have also found out about the world that might help you. Okay? But that's an abstract name. It's just, two ravens. It sounds, the URL had not been taken, right? So here's the architecture for how two ravens works. Is that correct? This is a better one. This is a better architecture. This is an architecture that's closer to what this is actually really the architecture that we use for the two ravens interface. And so what we have here is a thin layer. This is the front end that a user will actually see. A user themselves are going to see an interface, something on a browser perhaps, that they can interact with. And from that, they can say, I would like to know what data sets exist in Dataverse. So at an application layer, here's the big expansive code that exists in Dataverse and all the instance itself that handles the storing and preserving and metadata of a data set. And so a user can say, OK, I would like to talk to Dataverse and find out what data sets exist here that are private, that I can't see but I can interact with. And I would also, when I found a data set I'm interested in, I might like to ask a query to it. What's the mean of this variable you tell me is in this data set? Okay, so I can make queries to the data set, and the queries themselves, again, are not at the user layer. So I am not taking a data set and downloading it to the user layer and running a computation. I'm saying I have found at the application level that there is a data set that I'm interested in. I would like to make a query to it at the survey layer level. Go and get into that data set that you're not going to allow me to see, and can you give me an answer to a question that would be useful to me as a researcher? Okay, so at the server layer, where it might be protected, the data is stored. We're going to talk to R running on an Apache server, so we're going to talk to a web instance of R. That might make some calls. OK, you want a mean, you say? OK, let me see if I have an ability to construct a mean in a differentially private way from all the different things that I know how to do because different interns have written different pieces of code for this library. Yes, there is a mean there. Let me talk to Dataverse and find out what the mean is, if that exists, if that's been computed for that particular variable, stored on the, in a private way attached to that data set in the metadata, perhaps. Is there a private mean that's already been generated for that data set? If there is, OK, then you can have it, and we pass it back to the user. What's important here, and maybe we also have to talk to Zelig to find out how to do a regression or something like that. But what's important here is that we have this interface layer, and unlike RStudio or SPSS or Stata, we're not actually touching the data itself. We're asking questions of the data. The data is sitting in a secure server layer. We're speaking through an intermediary application, but we ourselves are not touching the data. Okay? Here's an example of what the, let me just see if I can pull this up. It's a lot of load today. Here's Dataverse. Here's a data set that you'll probably want to play with eventually. It's one of the key test data sets we've been using. This is a 5% random sample of census reports, census answers from California. If I click on this, it will say, oh, look, here is a small version of the data set that I've allowed to be explored. If I press the Explore button, okay, here's the two ravens interface, and it doesn't scale very well on this very small projector, which is my problem and not yours. But let me see if I open it up this way. No, that doesn't help too much. Okay, so here are some of the variables that it's chosen. I don't really like any of those variables, so I'm going to get rid of some of those variables. I'm going to say, maybe I'm interested in predicting what your income is out from, say, your age and your education, or maybe your gender. So I've thrown those variables into my model, and unfortunately, I can't see them all at the same time right now because of some scaling issue. But again, I'm going to start to play around with the data. I'm going to say, oh, look, here's income. What's going on in the income in my data set? And scaling issue. Let's see what's going on. Here's income. It's got a mean. It's got a median. It's got a most frequent observation. It's got a standard deviation, this many valid observations in my subset. Here's a bunch of summary statistics. You can understand whether that's the variable you thought it was, whether income really has the distribution you expected. Here's a little plot of it. It's heavily right-tailed. Few people are making a lot of income. Most people are making moderate income. And then maybe I can construct a model and say I'd like to explain income as a function of age and education. And then perhaps if we get private regression by the end of the day, I might say, oh, that's a model I'd like to run. Let's think of income as my outcome variable, my dependent variable. Let's run that model. And it's going to report back, OK, so here's a regression. I'm going to predict income as a function of age and education. The older you get, every unit of age you have, that's an extra year. Every time you celebrate a birthday, you're going to have an income that goes up on average by about $300. And as your education goes up 1 unit on this scale, it's going to go up 3 times 10 to the third dollars, so $3,000 as you get each unit of education. I'll tell you that this is a linear model, so it assumes that as you get older and as you get better educated, you get paid more. But that's, this is probably a nonlinear process. If you go to graduate school and then get more education, your income's going to plummet precipitously. Okay, but this is the interface that we've constructed for, again. Nothing here on this browser knows what a data set is or knows what a statistical model is. It's just an interface for saying, what would you like to know about this variable? What can I tell you? What kinds of models are you interested in running? The data itself is staying in Dataverse. And if it's private data, hopefully it's a secure instance of Dataverse that nobody else can see. The modeling itself is occurring on a remote server that I'm talking to, but I'm not actually running any models here. And so this is the interface. When we've talked a lot about an interface for private tools, this is one of the key interfaces that we'll be developing. And as you add new components to it, new features should hopefully be added to this interface. Okay. Any questions? Yeah.
Is this analysis a real analysis?
Yeah, that's analysis on a subsample of 2,000 census observations.
Then I think I don't touch the data, isn't it?
I'm sorry?
If it is real, then the two Raven touch the real data.
Okay, so the client, that is the browser that I'm looking at, hasn't touched the data. But it has said, I'm interested in running a model on income as a function of age and education, and said that that's the model I'm interested in constructing, sent that to R remotely. And on the server said, okay, well, then if I'm going to run that regression, I need to see the data. The server has touched the data and run the model on the server end, and then reported back, okay, I'm not going to tell you what the data is, in this case, but I can tell you that these are the coefficients that I estimated on the data. Does that make sense? Yeah, yeah, that's a good way of walking through the interface one more time. Yes? Sure. What, sorry? Yes. That would be good to know. Yes. Ideally, if I had better, so things like units are normally something I look to the code book for, right? So in the code book, it should say, this is a scale, education is a scale of 1 to 14, and 13 means you have some postgraduate work, and 12 means you graduated from college, right? That's the kind of information that should exist in the code book. If the code book exists well, then that information could be harvested and put into the metadata. And if it exists in the metadata, then we would see it in the summary statistics here. Okay? However, it's a case that when I uploaded this little test snippet of data, I did not upload enough information to populate the metadata. So if that existed, it would be towards the top. It would explain what the units were. But I don't know what it is in this case. And that's why metadata is so important. If you're thinking about an automatic way of dealing with a repository, if there isn't enough information in the metadata to make sense of what the data actually means, then you're grounded. Right? And that's why the first day of this conference is entirely about how do we construct metadata so repositories can talk to each other and we can do things automatically across repositories without having to read code books. Okay. So that's a great question. What's the mean of gender?
The average gender is 0.5.
Yeah. That's true in most census districts, but not all. There are some that are like 0.9, 0.95, and if you ever go to a women's prison, that will be your census district, and that will be the mean of gender in that particular district. Yes.
As far as the two Ravens jurisdiction goes over restricted data sets, can it see, for example, like restricted data sets metadata or even summary statistics?
Okay, so a lot of this is very much at a prototype phase. When Jack talks on Friday, he will guide you through the way the prototype currently works, and there's always big distinctions rather, between how the prototype currently works and what we envision the architecture to be, right? So yes, I will talk in the affirmatively, as in we should be able to see the metadata, and anything that exists in the metadata should be a privacy-preserving form of information. So there is an architecture where we say, let's construct a version of the metadata that only contains privacy-preserving statistics. So if it's got a mean in there, it's not a real mean. It's a privacy-preserving mean, a mean with some noise added to it, perhaps. And that's the kind of information that I can directly populate two ravens with. And then there are questions, as some of the people who are working on different projects are going to talk about interactive queries, whereby I want to know something that's not already in the metadata. I want to know something new, or I want to add something to the metadata, or add something to the set of things that I might know. And that's again a more involved question. So their two ravens is actually eventually through the server talking to the data and running a model on the data too. So that's an active problem in the architecture. But generally, it only talks to the metadata. Okay. Any other questions? I've run long, but that should be a good grounding of our tools. I will talk tomorrow mostly about how to use R, because a lot of us will be using R, but obviously you're welcome to, people who aren't using R but want to see R can see some of that. We have a break now, yes. I understand. Can I just say structurally, those of you who are working, did you want to talk at all about like the pragmatics of offices and things? Because this is a very good moment for people who need keys to this building to get keys to this building during this break, because Cassie is around. Is that something?
Yes, now would be a good time.
Okay. All right. So I understand that there are offices distributed across the campus for different people. If you are going to be working a lot in IQSS, then you should get a key for the office that we've constructed for the RAU students.